This second introductory video is about frequency and how it is related to the time period. Frequency can be defined as the number of waves passing a fixed point per second. This slinky shows a low frequency and then a higher frequency as more waves are produced per second. Frequency is represented by a small f and is measured in hertz. The unit hertz is abbreviated as a capital H followed by a small z. It actually stands for per second. So 1 hertz equals 1 wave per second. Let's look at another example. These two buttons are blinking at different frequencies. The one at the top blinks once every second, so the frequency equals 1 hertz. The one at the bottom blinks twice every second, so its frequency is 2 hertz. Let's look at frequency in the context of sound. I will play two tones of different frequencies and then look at the recorded waves. You notice already that the higher the frequency, the higher the pitch. I've recorded both tones in the background. Let's look at the results. This program called Audacity allows me to zoom into the waves so I can see what happens on a smaller scale. Here at the beginning I have a tone of low frequency, which then changes to the higher frequency. You see that there are more waves per time frame for the high frequency. Simply ignore the fact that the amplitude for the higher frequency turned out to be higher. Using the timeline at the top, I could now count the number of waves in 1 second, the frequency. In the last video, you learned about the time period. Let's look at how it is related to frequency. Let's go back to the buttons. The top button blinks once per second. From one blinking to the next, it takes 1 second. So its time period is 1 second. The lower button blinks twice every second. So it blinks every 0.5 seconds. Its time period is therefore 0.5 seconds. Using this simple example, let's have a look at the maths used in a more formal way, so we can apply it in any situation. The time it takes from one blinking to the next is simply 1 second divided by the number of waves I have in this second. In physics terms, the time from one flash to the next is the time period capital T. It is 1 second divided by the number of flashes per second, the frequency f. Rearranging gives me small f equals 1 over capital T. To get the frequency in hertz, the time period needs to be given in seconds. To make it even clearer, let's look at goats. Say the goats are running past you in a single file. Every goat counts as 1 wave. If you have 5 goats running past you every second, then it takes 1 goat to pass you 1 second divided by 5 goats equals 0.2 seconds. In physics terms, the time period t equals 1 second divided by the frequency f equals 1 over 5 equals 0.2 seconds. Let's see how this can be applied to sound. I'm generating and recording a sound wave of 200 Hz. The reading for the trough of this wave is 4.87 seconds, and 2 waves later I get 4.88 seconds. That makes a difference of 0.01 seconds for 2 waves. My time period would therefore be half of that, 0.005 seconds, or 5 milliseconds. Now I can calculate the frequency. The frequency f equals 1 second divided by the time period t. Here this equals 1 over 0.005 equals 200 Hz. As expected from the settings of the tone generator, 200 waves are reaching your eardrum every second when you hear this tone. Let me summarize. In a nutshell, frequency is the number of waves passing a fixed point per second. It is represented by the small letter f and is measured in hertz. The frequency can be calculated from the inverse of the time period. To obtain the frequency in hertz, the time period must be calculated in seconds. In the case of sound, the frequency is associated with pitch. A high frequency sound will have a high pitch and a low frequency sound a low pitch.